Okay, in this video, we're going to talk about nuclear magnetic resonance spectroscopy. In this video, we're going to talk about the science behind how NMR works, and then in additional videos, we'll talk about how we can use NMR to characterize our molecules and how to interpret the spectrum. So, nuclear magnetic resonance spectroscopy, or NMR, is maybe one of the most powerful methods for gaining structural information about molecules in organic chemistry. And NMR involves interaction between electromagnetic radiation and the nucleus of an atom. And we're going to focus on carbon and hydrogen nuclei, and I think that may be obvious for organic compounds. And we're going to use the fact that the structure of a molecule uh, changes how the nuclei interact with the radiation. So this is just a reminder about the electromagnetic spectrum. It includes things like visible light, ultraviolet, X-rays. We talked previously about IR spectroscopy, where the vibrations of molecules interacted with infrared light. In NMR spectroscopy, we're going to talk about how the nuclei interact with radio waves. And so this is a slide that I had on the IR introduction as well. And so, different types of electromagnetic radiation interact with molecules in different ways. Infrared has to do with the vibrations of molecules. In Gen Chem, I think in the labs, if you took them at GGC, you would have used the UV-Vis spectrometers, where we were causing electrons to move into different orbitals. And when we use NMR spectroscopy, we're going to cause flips of the nuclear spin. Now, in general chemistry, you would have learned about spin as it relates to electrons. And spin is a fundamental property of many subatomic particles. It's what's called an intrinsic magnetic moment. It actually makes them behave kind of like little magnets. Now, despite what the analogy that many people like to use that is an incorrect analogy, electrons, as we'll learn, protons and neutrons are not actually spinning. The spin refers to their interaction with magnetic fields. And in Gen Chem, when we would have drawn an orbital energy diagram for an element, in this case iron, if you remember, when we put electrons into orbitals, when we would draw these orbital energy diagrams, we would draw one arrow up and one arrow down, and this represented the spin of the electrons, right? When the arrows were pointing up, they had spin up or alpha spin, and when they were down, they had beta or spin down. And electrons, when we put them in the same orbital, had to have different spins, and that's why in all the doubly occupied orbitals we have arrows that are up and down. And I mentioned that spin has to do with their interaction with magnetic fields. I picked iron on purpose to show the orbital energy diagram because it is in large part, or I guess entirely, due to the fact that iron has all of these unpaired electrons that have their spins pointing in the same direction that gives iron its magnetic properties. So, just like electrons, it turns out that protons and neutrons also have spin. And if the nucleus has an odd number of protons or neutrons, then the nucleus overall will have a net spin. And some examples of nuclei that have a net spin are things like regular old hydrogen, or the isotope of carbon that's carbon-13, right? Most carbon is carbon-12. That has 6 protons and 6 neutrons. So carbon-12 does not have a net nuclear spin, but carbon-13 with 6 protons and 7 neutrons does have a net spin. And these are some other elements that have net nuclear spins. And so in these cases, when I have an odd number of protons or neutrons, the nucleus overall will behave like a tiny magnet. And that means it will interact with the magnetic field. So normally, the nuclear spins are disordered. And so we're going to use arrows to represent the direction of the magnetic moment for the nuclei, just like we did for electrons. And so normally, the nuclear spins are disordered. They can be pointing in any random directions. But if we apply a magnetic field to our sample of nuclei, the nuclei will align themselves with the magnetic field either in the same direction or in the opposite direction of the magnetic field. And it turns out these different orientations have different energies. And the spin state that is aligned with a magnetic field that we call the alpha spin is lower in energy than the beta spin state that is opposite to the applied magnetic field. And so it turns out we can cause the spin of electrons to flip. So this difference in energy, if I hit it with a photon of electromagnetic radiation that is exactly equal to the difference between the energy of the alpha spin state and the beta spin state, we can cause this flip. And that sample will absorb that frequency or wavelength or energy of electromagnetic radiation. And it turns out that different nuclei have different numbers of electrons and other nuclei around them. And that actually changes their magnetic field, and it changes how they interact with the magnetic field that we apply to them. As a result, different nuclei have different energy gaps between their alpha and beta spins when we put them in magnetic fields. That means that different nuclei will absorb different wavelengths. So different wavelengths are required to cause these spin flips. And so here's just a simple example. This is propanol. And so it turns out these protons here that have an odd number of protons, they are, if I apply a magnetic field, that will cause a difference in energy between the alpha and beta spins, and it will take a certain amount of energy to cause the electrons to flip. And so to cause that flip will require absorbing a particular wavelength or frequency of radio waves. It turns out the methyl group on the end has a lower energy gap, and so they will absorb a different frequency or wavelength of radiation. And so in NMR spectroscopy, what we do is we apply a magnetic field to our sample, and that causes the nuclei to align, and it causes the alpha and beta spins to have different energies. We then shine all different types, such as we scan through different wavelengths of radio waves to see which ones are absorbed. And depending on the frequency at which the radio waves are absorbed, that tells us something about the molecule. And as we're going to learn in the other videos, right, how do we relate the NMR spectra to the molecule, or how do we rate the molecule to the NMR spectra? And as we're going to learn, uh, this signal here corresponds to the methyl group. This signal here corresponds to the ethyl group. And the signal down here on the end corresponds to the single hydrogen down here. And so in the rest of the videos, we're going to learn how to interpret these NMR spectra and how that relates to the molecular structure.